Okay, let's do the second part of this problem. So in the previous video we defined geometry, applied material properties, defined our boundary conditions, and meshed. So those are basically the key steps required to set up this problem. Now we're going to go through and actually solve it and get results. So if you left click on this arrow under study, bring up the time dependent problem, you notice the default goes from a time equals 0 at 0.1 second increments up to 1 second. So we're going to leave that as our default settings and solve. So if you right click on solve and left click on compute, it will go through and do a number of time steps and give us a final solution. Alright, so here's our temperature gradient. So you notice most of the thermal gradient's up near the top, so this heat transfer hasn't propagated all the way through and reached steady state. But it is good to note that our boundary conditions, 293 on the bottom, 350 on the top, are satisfied. Let's go down to the isothermal contours. So you notice here, large thermal gradients, these arrows correspond to the heat flux. So remember that is, the arrows are proportional to our thermal gradient. So to make this a little easier to see, we make these arrows a surface. So if you right click on isothermal contours, I want to add a surface, and I want to look at heat transfer in the y. So if I type HT grad TY, and then I believe that we have to right click and plot. Yeah. And I'm going to drop the contour. So if you right click on contour and delete, are you sure? Yes. Okay. So now we've got temperature superimposed with heat flux, right? So most of this is a highly transient problem. Everything's occurred at the beginning. Well, I want to compare this to steady state problems. It turns out for a steady state problem, you should get a factor of 2 here on your heat flux. So let's look at this carefully. Let's go back to our time dependent, and if this heat transfer propagates further in, and as you would expect it does. If I look at this, it's propagating down. Still not clear if it's propagated all the way to steady state. One way is you can plot a movie. The other is you can continue to update this until the solution doesn't change anymore. Then you know it's a steady state. So I've increased the final time to 300 seconds. And here's what we get. Let's look at our surface, and here's what we're seeing now. Alright, so if we come over here, I think we can left click and it'll give me a value of 57. Here it's 100. Turns out theoretically it should be twice the heat flux at this point versus here. Reasonable but not exact. So to make sure, let's increase this one more time. Let's go to 400. Let's go a delta T of 20, 103, 57. Okay, so reasonable. It may be an issue with our mesh. We can go back and look at that, but this gives you an idea on these properties. So let's stop here.